Welcome everyone. Today's lesson is entitled Exponential Functions and the Number e. This is a follow-up to the introductory lesson on exponential functions. So we're going to expand on some of the concepts we learned in the previous lessons, and we're going to explore a brand new number. So we'll see how that plays out. So I do need you to grab your graphing calculators. If you can do that right away, we'll start with the investigation 1 on your paper. And it says exponential growth and decay graphs. Use a graphing calculator to graph several exponential functions of the form y equals a times b to the x, and then provide conclusions to the following. All right, perfect. I'm going to bring up my graphing calculator here, and you can just play around with it. I'm going to do basically the same up here. You can do similar ones, you can do the same ones. Does not matter to me, but just going to do y equals a times b to the x, and I'm going to keep the numbers really simple because I'm just going to use the standard window, as you'll see momentarily. So here's a good one just to start with. So I'm going to do 1 times 2 raised to the x. So a is 1, b is 2, and I'm just going to go ahead and hit zoom and number 6, and hopefully something pops up there. There we go. And we see our first exponential growth curve. So a couple things to keep in mind as you do look at these graphs and try to form some conclusions. And by the way, as I do have that graph up, let me go over a couple of these characteristics that we want to look at. So I want you to think about domain, I want you to think about range, horizontal asymptote, the y-intercept, and then this is a good question as well. Is the function, excuse me, 1-to-1? All right, now a couple things I do want you to do to get this going, because it's tough to see the entire graph here. So if you would hit the trace button for me, and by the way, there's the y-intercept, and you can see the y-intercept at +1 here, and I do want you to make one quick connection right away. Look at that one right there, and that right there. No coincidence, as we'll see. But more importantly, I want you to trace it out, and so I'm just going to hit the left arrow. And you can see, even though the graph is, it's tough to kind of tell in here, the graph does continue to the left. And I can keep going and going and going forever and ever and ever there to the left. X is going to get large negative, meaning it's going to keep going to the left. And those y values are going to get closer and closer and closer to 0. Do you think they're ever actually going to hit 0 or cross 0? And the answer is no. All right, so again, you can play around with this a little bit. I don't want to take too much time, but do want to get a sense of what an exponential growth curve looks like. I'm going to go back to my y equals, and I'm going to play around a little bit. I'm going to do 2 times, how about 1.5 raised to the x, and now I'm going to hit graph. And notice we get the same type of exponential growth curve, not quite as steep, because our b value is a little smaller than the last one. Do you want to go ahead and see that y-intercept? Look, here's the y-intercept at 2. And look at the a value, everybody, also +2. Keep that in mind. And same deal, I could scroll to the left. And you'll notice again, x is going to get smaller and smaller and smaller. And the y values are decreasing, but they seem to be plateauing towards 0, and so forth. Cool. All right, don't want to do too many more here. I actually just want to maybe do an exponential decay model and then kind of come up with some conclusions here. So I just did that one. So same idea, 1 times 1/2 raised to the x. Remember, if the b value is in between 0 and 1, it should be exponential decay. What does that look like graphically? And so what we have is our first look at what's called an exponential decay curve. And so rather than doing this, it does that instead. And I'm going to hit trace one more time. And y-intercept, +1. There's the a value, +1. Shouldn't be a surprise there. And as I come off to the right, now in this case, x is going to get large positive. And when it does, notice the y values are getting closer to 0, closer to 0. Are they ever going to actually hit 0? No, no, no. All right, I think that's good for now. Let's fill in what we know. And let's actually go in this order. Let's do the y-intercept first, because I was harshing on that for a little bit. So long story short, the A value represents the Y-intercept, and you saw that on the 3 that I did. Maybe you put different ones in, but you should have seen that as well. Whatever the A value is, that'll be the Y-intercept. Now the domain and range are the ones I really want to talk about, and if you noticed in each case, be it an exponential growth curve or an exponential decay curve, you notice that I was able to trace going to the left forever and ever and ever, to the right forever and ever and ever. There was no discontinuity anywhere, and so as a result, the domain of every exponential model is all real numbers. So I can put any number in for x and have that as the exponent and raise that to that power. So any type of number will satisfy being the exponent, but my answers, my range, my outputs will not be all real numbers. So what we saw graphically in each particular case, growth and decay, is that the Y values were positive. Do you guys remember that? I'm going to bring it up one more time just to quickly illustrate. Look at the Y values, look at the graph. It's above the x-axis. Here they're shooting to infinity. As it comes down and we go to the right, they're still positive. That's still a positive number. And as it gets closer to 0, it will still stay above the axis. It will get infinitely close to the axis, but will never touch it or cross it. So as a result, everybody, that would be our range. No or equals. That's the key for this one, no or equals. Which means, we can fill in this piece, there is a horizontal asymptote at y equals 0. So the graph gets infinitely close, but never going to touch or cross. Excellent. Now this last question, is the exponential model y equals a times b to the x 1-to-1? Remember, for it to be 1-to-1, it has to pass the horizontal line test. You don't have to write that in there if you don't want to, but that's what we would be looking for. And I'll bring it up one more time. And it works for growth or decay. Does it look like these exponential curves pass the horizontal line test? Absolutely. Even though it's getting pretty close to horizontal as it plateaus towards 0, it still is going down. It's still descending ever so slightly. So, long story short, the answer here is yes. Which means if it's 1-to-1, then the inverse of these exponential models is a function. And what you're going to see over the course of this unit is we're going to explore the inverses of the exponential models. So that's why this question is kind of in this piece. All right. Hope that works for you. Let's move on to the next. So example 1, write an equation for each graph. And let's see, for A and B it looks like same scenario, but I did one growth and one decay. And then letter C is the really good tough one. So let's do A and B, and let's see how this shakes out. So first and foremost, these are exponential curves. The model that is going to fit these curves would be y equals a times b to the x. Let's see what information we have. Let's see what information we need. And we'll go ahead and do the algebra in order to solve for what we don't have. All right, so first order of business. This is an exponential growth curve. I do see a y-intercept right away of +4. And so without a whole lot of issue, everybody, I know based on the investigation that we just went through that the A value should be 4. Excellent. Now I have no idea how this is growing, so I don't know what the B value is just yet. And so as a result, that is the unknown. But what I do have is a very particular X and Y value that I can put in. Now remember, if it is a point on the curve, then it's going to make the equation true. And so as a result, I can use the X value of 4 and the Y value of 41.9904 to solve for B. And you've done this with a variety of other models too, substituting the point into the model to come up with what we need. All right, well, let's go ahead and do this. So I'll bring up my calculator. We're going to do 41.9904, and we're going to divide by 4, of course. So I'm going to do that here. Yeah, let's get that going. There we go. 41.9904. Divide that by 4, of course, and we get 10.4976. So I'm going to write that right here. 10.4976 equals b to the 4th. Excellent. Now, how do I undo raising to the 4th power here in order to solve for b? And as this operation has its opposite, we will employ that at this time, which would be the 4th root. That's not an h, by the way, guys. That's a 4. And so when I do the 4th root over here, those will cancel and I get my b. And now I'm going to apply the 4th root to my answer right over there. So I'm going to bring my calculator back on up. A couple ways to do this depending on if you have the TI-83 or 84. I think regardless, though, you still have to hit the number 4 first. And then you're going to go hit the math button. And you should see the x root right down there. So that is on my calculator, the 5th option. So what this is saying now is the 4th root of this number right here. And you can type that in. I'm just going to do second and an answer. So it's a little quicker for me. So the 4th root of that 10.4976. Excellent. And I get 1.8. So I get a b value of 1.8. Perfect. Hey, I'm ready to write the model then. We already had A. We have B. And there it is. Now notice, exponential growth, everybody, right? We saw that with the curve. Do you notice the b value is above 1? That should absolutely correlate with what we talked about in the previous lesson. Above 1, growth. So that's perfect. Let's go ahead and back this on up quickly with the letter b here. Now that this is pretty much the same exact problem, I'm going to run through it a little quicker if that's all right with you. Y-intercept, of course. Let's start with that. And I've got 24. Excellent. I have no idea how this is decaying, so I have nothing about the b value here that's going to help us at this point, but I do have an x and a y on the graph, and so I'm going to use that right here. So the x value is 5. The y value is 1.86624. Looking good. Now we're going to go ahead and divide by the 24, and then 5th root. So just undoing those operations. Let's see if we can go ahead and pull this off. So I've got 1.86624 and divide by 24 there. And so I get 0.07776. I'm going to write that on the board. Okay. Undoing raising to the 5th power means I'm going to 5th root. So everybody 5th root if you would. Let's see if you can pull off this on the calculator even before me. I'm going to go ahead and do that now. So I hit the number 5. I go to my math menu. And again, it's that 5th one down right there. And I'll just do it as the answer. And I get a b value of 0.6. Fantastic. Alrighty. Ready to write the model. And then I'll just highlight one thing about this one before moving on to the hard one, which is letter C. All right, we've got that. Now notice, this was an exponential decay curve. There it is in all its glory. Notice, look at my b value, everybody. In between 0 and 1, just like we would expect. Cool. Let's go get part C, which is a little harder. What makes this one harder is I don't specifically have that Y-intercept. Now I know you're saying, it looks like 2, it's got to be 2. But you know what? Can't be trusted based on this situation unless it's labeled. So yes, it may be, but I want to do the math to see that. Because again, this is a pretty thick line. For all I know, it goes a little above or a little above the 2, or below the 2, excuse me. So we don't know. Long story short, I only have 2 points, neither of which is the Y-intercept. So the 2 labeled points here Neither one is going to be letter A. I have nothing about the growth rate here. So here's the problem with this. And I'm going to write y equals a times b to the x to kind of get this moving along. When I put in an x and a y, I mean, that's all great. So I've got that. A and b, as I said, in terms of what's labeled, that's unknown. So what I have when I substitute that in, sorry about that. What I have is an equation, but unfortunately 2 variables with it. And that doesn't do me a whole lot of good. I've got nothing to really solve for at this point and get a numerical value for. Come on. Yeah, my board seems to be acting up a little bit. Let's see if I can plow through it though. But what I need to do in this particular case is also use the other point. So in essence, I can create another equation with x and y that also has the same 2 variables. And you've seen this before in different contexts. It's basically 2 equations in 2 variables. So how do I solve 2 equations in 2 variables? Well, if you remember from Algebra 1, we could do elimination, we can do substitution. Now either one actually works out really nicely here. I'm not going to go through the elimination method because that's inherently different than what you've seen with linear equations, but I'm going to do substitution because it's basically the same exact math. So the situation here is 2 equations, same 2 variables. Solving for a and b, here they are in both. All right, so the idea, I guess, is I'm going to get the a by itself. Easiest thing to do. I see it right over there. That's all well and good. And I'm going to take this expression for a, and I do a lot of circling and drawing arrows and all that fun stuff, but essentially I'm going to replace that in the other equation. And so we're going from 2 equations and 2 variables to 1 equation and 1 variable. So I'm going to rewrite this, and instead of a, I'm going to write it as, what's that, 1.33 over b to the negative first, and then of course times b to the third. And now if you notice, it's a single equation, of course, in a single variable, which should allow us to solve it. So if I clean up the exponents, again, just good old-fashioned exponential properties from way back when, I get 1.33 b to the third divided by b to the negative first. Remember, when you divide powers, you keep the base and you subtract the exponents. 3 minus negative 1 is 4. Awesome, and then this is looking exactly like a couple of the previous ones that we've gone over. So I'm going to go ahead and divide by that 1.33 and then 4th root it. Let's see what it gets. So 6.75 divided by 1.33, got that. And I'm going to do the 4th root of that answer. And even though it's not precise there, we're going to call this 1.5. So b value, 1.5. Excellent. Now, that's all well and good. The problem was, in this particular case, we didn't have the a value like we did in examples a and b. So we need to find it. So I'm going to take that 1.5 and I'm going to put it right in there. Seems like a good spot for it. And when I do you see that'll solve for a? So one more time, 1.33 divided by 1.5 raised to the negative first. And again, this is meant to be 2, by the way. And as I said, I know it was right there, but couldn't trust it. So I'm going to say a is 2, and we're going to write our model. Y equals 2 times 1.5 raised to the x. So given 2 points, neither one was the y-intercept. We need to do a system of equations in order to get a and b. Awesome. Let's keep it moving. All right, so the next piece, and it looks like an investigation here, is to actually look at this new number that we're going to talk about, the number e. And the way we're going to try to do this is really calculator heavy. We're going to take a look at this expression right here. So 1 plus 1 over n raised to the n. And what we're going to do is allow n to get large and see what happens. So notice I'm going to start out very small, 1, but I'm going to start to build up pretty quickly there. We're going to put larger and larger numbers in. So in just a couple steps, I'm going from 1 all the way up to 100 million. And so watch what happens to the output, the value of the expression when we do this. So it's kind of cool. All right, so grab your calculator, I'll grab mine, and I'm going to do 1 plus 1 divided by 1. Close the parentheses, raise it to the first. This should not be a shocker, but you get 2. All right, so that's all well and good. Now I'm going to probably do just 1 or 2 more of these and then just write the others in, but maybe you're working a little quicker than I am, and you can just kind of write them in and wait up for me. But the next one, now when n is 100, so 1 plus 1 divided by 100, close it, raise it to the 100th, and notice, get something a little bigger. So let's write them all out here, and you'll see why in just a sec, but I've got 2.704, 813, 829. Okay, very good. I'm going to do one more. So now I'm going to jump up by another factor of 100 all the way up to 10,000. And 1 plus 1 divided by 10,000. Close it, raise it. So what's kind of interesting about the expression is when you do the inside, that's getting smaller and smaller and smaller, but you're raising it to larger and larger numbers. So what happens to the overall value of the expression? Notice in this particular case, it went a little higher, so I got 2.718145927. All right, now obviously I could keep going on the calculator with you here, but I don't want to use our valuable time to do that. I'm going to write them in and watch what's going on here as n is getting really large. I went from 10,000 to 1 million, and 1 million to 100 million, and watch what happens to the value of the expression. Does it increase dramatically or barely at all? So I'm getting this when n is 1 million, and look how far back I have to go just to see any change. I have to go 1, 2, 3, 4 decimal places back just to see any type of change. Even though I went from 10,000 all the way up to 1 million, it barely changed the value of the expression. We have to go pretty far out just to see it. And then when I do 100 million, so I'm going from 1 million to 100 million, I get this. So 718281815, and let's see, in this case, I changed by 99 million, literally, from going from 1 million to 100 million. And look how far back I have to go just to see any change there. 1, 2, 3, 4, 5. I have to go 6 decimal places back just to see any type of change. So it kind of begs the question, is there a limit to your answers, or are your answers increasing without bound? Are the answers skyrocketing, or do they seem to plateau towards a particular number? And of course, there's a limit. They are approaching a particular value. And so, without further ado, as n gets infinitely large, the values of this expression approach the number e. And one definition of e, and we haven't gone over this notation, but this lim right here means limit. So you're taking the limit as n approaches infinity. So as n gets infinitely large, those values approach e. And so e is the limit as n approaches infinity of that value of that expression. Okay, pretty cool. So e I'll try to make a long story short, and then we'll kind of move on with the examples that we're going to do with this. So E, very simply, is a mathematical constant, meaning its value is fixed by an unambiguous definition. And like pi, kind of think of that, you can have that as an association if you would. Like pi, E is an irrational number, meaning it cannot be written as the ratio of two integers. So you've seen irrational numbers before for sure. And it's what it's called transcendental. So it's a transcendental number. And transcendental, again, long story short here, means that it's not a root of any polynomial with rational coefficients. And I'll be super quick with this. Again, I promise. I know I've said that already 3 times. So all different types of numbers. And if I had something like this, here is a polynomial with rational coefficients. 1 there, 4 here. And if you solve this, of course, you would get integers. You'd get plus or minus 2. Those are 2 types of, those 2 and negative 2 are integers, a particular type of number. Okay, if I gave you something like this, okay, and I solved that, okay, this is a polynomial, rational coefficients, and if I solve this, I get an I get a rational number, just not an integer, my bad there. I get a rational number, I get 1/2. Awesome. Now watch this one. Here is another polynomial with rational coefficients. Again, here's a 1 and then there's a 2. So rational coefficients. If I solve here, I actually get irrational numbers. Okay. Now, E is different. E is irrational, but it is also what's called transcendental, meaning I can't create an equation like this with rational coefficients and get E as an answer. I can get an irrational number, but I can't get a transcendental number. Again, I went through that relatively fast, and there's a lot that goes into it, but don't worry about it. For our purposes, E is going to be used in the context of our exponential models. We're going to see an application of it in the very next lesson. But for right now, I know I'm going to do it on the calculator in just a second, but this is what we're after in this particular case. E is widely used as a base for exponential growth and decay functions. Again, we are going to see an application of it in the next one. But I want you to kind of get used to the idea of seeing it as the base of an exponential growth or exponential decay model. All right, before I go any further with that, let's grab the calculator, please. And this is the button you're going to be using. So I'm going to have you do E on the calculator, and it'll give it to 9 decimal places. So go ahead and hit the second button for me, and then you should see the LN button, which has a relationship with E, and as we'll see. But go ahead and hit that one right there. And notice that button, it's used so often as the base to an exponent that, again, it has its own function on the calculator as a result. In this case, I'm just going to do E to the first in order to get E. And by the way, do you notice, isn't that a little larger than what we saw previously with our answers in our investigation? So again, E on the calculator, 2.7128281828. Coincidence, by the way, that it's repeating. It is still irrational, meaning after this, it doesn't just repeat that pattern. So ... because it is irrational, meaning those decimal places go on forever and ever and ever, and never repeat. Okay. Let's go examples 2 and 3 super fast, and then get into a couple applications with base E to wrap this on up. So first and foremost, y equals e raised to the x. And without a whole lot of issue, everybody, if I graph that on the coordinate plane, is it going to be growth or decay? Remember, E is a constant. We have the decimal approximation of that constant right here. Is that above 1 or between 0 and 1? Well, above 1. So it has to be growth. Absolutely. Now I'm going to go ahead and graph this super fast here, getting used to just using our E button. So y equals second e raised to x. Zoom, number 6, and we should see a nice looking exponential growth curve. Looks great. Sketching it looks something like this. So again, kind of like that. Domain, all real numbers. Y-intercept would be 1 because of the 1 in front of it. Growth because this is a number above 1. And horizontal asymptote at y equals 0. So nothing really changes there. Awesome. Now, example 3, use transformations to sketch y equals e to the negative x. So we know what e to the x looks like. Do you remember the transformation going from replacing the x with negative x? Should be a y-axis reflection. And why in the world did I put that there? Because if I reflect it over the y-axis, it ceases to be exponential growth, and as you can see, of course, becomes exponential decay. So how do I get a base E graph to be exponential decay? With the negative with the exponent there. So let me just quickly show that to you. So again, e raised negative, use that button right there, x, graph it, and you should see, of course, there's our exponential decay. So in base E, if there is a positive up here, just straight up exponential growth. In base E, if you see a negative, decay. Super. All right then, everybody. Let's get into just our last couple examples. Again, for right now, all you're thinking about is exponential models can be written in this new number, this base E, and all you're going to do is utilize it. Again, the context for it we will continue to develop over the course of the unit. Specifically, you'll see tomorrow, if you've looked at tomorrow's lesson called Compound Interest, we'll see a context for it there. But again, just for right now, you're just getting comfortable with the idea that there is a number E. It is used as the base in an exponential model. It would be growth if it's positive up here, as you see in example 4, and it would be decay, as you can see with the negative in example 5. All right, example 4. India is currently one of the world's fastest growing countries. By 2040, the population of India will potentially be larger than the population of China. The exponential growth model, P of t equals 1.014 times e raised to the 0.0158t, describes the population in billions T years after 2000. Well, what was the population in 2000? Should not come as a shock that that number in front of our base E is the initial value, would be the y-intercept on the graph. So it would be 1.014 billion. Make a prediction about India's population in 2040. Again, nothing doing, guys. It's just a function. Inputs and outputs. The 2040 would represent a time value, so it's the input of this function. So just be careful, though. Obviously, if we're starting in 2000, it would be 40 years. So I'm going to do 1.014 times e raised to the 0.0158 times 40. And again, all of that will be up in the exponent. We're going to let the calculator do the work. Okay, input of the function. Let's come up with the output of the function. So I'm going to grab my calculator, and again, you're just getting comfortable with this button right here. So second, and then that ln. So e raised to, notice it knows the context for using base e. It knows that we need to raise it to something. So 0.0158 times the 40. I'll close that on off, but that should be looking pretty good. And I'm getting close to 2 billion here. So I'm going to write it off to the side. So P of 40, input is 40, output would be 1.9077. And again, I'll just throw the billion on the back as the model's in billions. Okay, next piece. China's population can be modeled with the function of this, P of t equals 1.262 times e raised to the 0.009t. Notice this number smaller than this number up here. So that is a particular type of growth rate, and the growth rate in China is smaller than the growth rate in India. So that's the idea behind this, is one population should catch up with the other based on the growth rates. So we're going to do this just with a graphing calculator here. And I'm going to give you just the window to use. Again, I don't want to take too much time on this. It's just calculator work at this stage. So everybody, I'm going to put in 1.014 times e raised to the 0.0158x. That'll be in y1. And then everybody, I'm going to do the model for China, 1.262. And then again, times e raised to the 0.009x, looking good. Everybody hit window for me if you would. I just kind of looked at this. So we're going to go 100 years out into the future. So starting in the year 2000, going out 100 years. And because this is in billions, I'm going to start it at 0. And looks like on my paper I just have up to 3 billion. Shouldn't even be that high, but let's go ahead and see these exponential growth curves. So that one's the India curve, and this one is the population of China curve. Notice, started out higher, but is growing more slowly. So at some point in time, with the faster growth rate in India, catches up. Now we're going to do, I think actually we've seen stuff like this before, where if I need to find where they intersect, I go second trace, and number 5 there is intersect, and just hit enter, 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 and looking pretty good. So it looks like about 32.18 years should put us at about 2032 according to the model. Again, those growth rates potentially have changed over these last many years, but based on this data, that's the possibility. All right, let's get into the last part, example 5. So just an example of an exponential decay model, base E. Notice the negative right there. That's what illustrates its decay as opposed to growth. So normal healing of wounds can be modeled by an exponential decay function. If A sub 0 represents the original area of the wound, then the area A of the wound after n days can be modeled by this function right here. Perfect. If healing has taken place, how large will the area of the wound be after 3 days? Again, no worries, everybody. We're just, think of this as input and output. Now, I didn't write A of n here in terms of like good old-fashioned function notation, but I'm going to do it here. Essentially, we're looking for an input of 3. And it does say use 1 for A sub 0. You could use 100 too, kind of think of it as a percentage. But again, don't worry too much about it. All I'm doing is that. Again, just getting used to the prospect of using base E for exponential growth and decay. And again, we'll look at a variety of applications and uses for that over the course of the unit. All right, so I've got 1 times E raised to the negative 0.35 times 3. Again, when I use that button, it automatically raises because it was a base. And so getting about A equals 0.35. So if the wound had an area of 1, then now it has an area of 0.35, which would be, just kind of thinking about it as how we want to interpret the wording here, I would just say it's 35% of the original area. That's good enough. And lastly, letter B, use a graphing calculator to determine when the area will be 1/10 of the original area. So in this case, everybody, I'm giving you an output, you're coming up with the input. So we are going to be solving something like this algebraically. So sorry, this was 0.1, or actually let me write it as 0.1. So 0.1 equals 1 times e to the negative, and again, I'll just do it as 0.35 and something like that. Now again, to solve this algebraically is actually not too bad. We just don't have the background at this stage to do it, but very soon we certainly will. So when that time arises, it'll be easier than putting it in the graphing calculator. But for right now, everybody, I'm afraid that is what we have to do. So you're going to put that into the y1. And we've seen this before. I'm going to put this into the y2 and see where they intersect. I'll give you a nice window for it. And then we'll, as I said, wrap this piece on up. So clear, clear. Let's go to that y1. So 1 times e raised to the negative 0.35x. And lastly, just a 0.1 right there should do. And guys, hit window. I'm going to go 0 to 10 and 0 to 1 on the y, because think of that as 100% of the wound, and it's going down and down and down, never going to get below 0. And you can see that right there. Awesome. So there's my exponential decay, everybody. And again, because the negative value right here, that's what changes the base E from growth to decay. Let's intersect this. So second trace, hit intersect, enter, enter, enter. And I'm getting about 6.58 days. All right, everybody. So good continuation of the previous exponential functions lesson. We'll see an application tomorrow. And yeah, there's some great stuff with this. All righty, guys. Just let me know if you have any questions or concerns, as always.